Hello, dear professors. My name is Shuqi, and here is my student number. Today, I'm going to talk about a preliminary explanation of fractional order differentiation and its applications. Here are four parts, and the first part, I'm going to give a brief introduction, where the fractional calculus was proposed as soon as the ordinary calculus was proposed. It's also raised by the Leibniz that to generalize the derivative to the non-integer orders. Leibniz also said that it leads to a paradox from which one day useful consequences will be drawn. Nowadays, there are many different ways of generating the non-integer order derivatives, which leading to many different results. Is this what the Leibniz called the paradox? Well, for starter, I present an unified definition of the fractional derivatives here. It's been shown that when the fractional order alpha is larger than zero, the form of which is more like the differential operator, and when the order alpha is less than zero, it's more like an integral. When we are going to construct a fractional derivatives, we expect that the derivative should approach the original derivatives when the order is an integer. It's just like the figures showing. And in my work, I'm going to compare the performances of two derivatives, the GL derivatives and the capital derivatives, on some simple functions, like the exponential, trigonometric, and the polynomial functions. Also, the fractional derivatives are very useful. It can be applied in various fields, like the physics, engineering, and other sciences. And it's been studied that the fractional derivatives capture the memory properties of the biological systems better than the integral derivatives. And in my work, I'm going to solve a fractional pre-predator models. It's also known as the fractional LV models. There are various numerical algorithms proposed, such as the reproducing kernel techniques and the finite differences method, and so on. And I choose to use the three-step Adams-Bedford method to solve this problem. It's very simple but a very effective numerical algorithm. And in the second part, I'm going to show something on the fractional order derivative. As we mentioned before, there are many ways to define the fractional derivatives, and I'm going to explore the GL derivatives and the capital derivatives here. Here I present the definitions of these two derivatives. The first one is the GL derivatives, and the second is the capital derivatives. And it is worth mentioning that when the fractional order alpha is the capital derivatives have no meaning when the fractional order alpha is an integer. Then I use the MATLAB to solve the fractional order of GL derivatives and the capital derivatives of some simple functions like the sine x, x squared, and exponential x. And I choose the fractional order alpha equals to 0.5, 0.2, and 0.8. And here I present the numerical results. The first line is the GL derivative, and the second line is the capital derivative. From the figures, we can see that these two derivatives are performed very well in the sine x and x squared. But as for the exponential x, as we expect, the fractional order of the derivative of the exponential x, it should be still itself. But in this case, these two derivatives are not matched. And also here I present animations in this website. It can be seen some notation of these derivatives in different fractional order. Also, there are some numerical results are presented in table in my paper. Now, let's back to our question. Why do the GL and capital derivatives perform poor in exponential x? There are some issues in these two definitions, and now we are going to analyze this in the GL derivatives and capital derivatives to solve this problem. For start, we are going to study the exponential functions in GL derivatives. In this case, we would set the initial point t0 equals to the negative infinity, and we can have the alpha order GL derivative of the exponential bt is the b power alpha and exponential bt, which is really equals to the normal derivative functions. And also by using a very famous formulas, we can derive the alpha order GL derivatives of the sine x and cosine x in this way, which also perfectly matches our figures before. As for the capital derivatives, we can solve the alpha order capital derivatives of the exponential bx as follows. But for the simplicity, when we choose the b equals to 1, it can be shown that any alpha order capital derivative of the exponential x is still itself, which also perfectly match our expectations. And similar to the GL derivative, we also present the sine x and cosine x of the capital derivatives here. So now back to our question, are these two definitions failure in the exponential x? No, the poor performances in the numerical result is because in the numerical result, we are assume the initial point t0 equals to a finite number, but when we are doing our analysis with solutions, we assume the t0 equals to the negative infinity. In this case, we change the range of our evaluation and get what's the result we are satisfied. And it shows that the fractional derivatives is a non-local operator. And next, I summarize some differences between the ordinary derivatives and the fractional derivatives. It's been mentioned before that the fractional derivatives is the non-local operator, while the ordinary ones is the local operator. And the integral derivatives can be seen as a discrete one, and the fractional derivatives is more continuous. In the third part, I would give some application of the fractional order derivatives. As we mentioned before, I choose to apply in the predator-prey models, and it is a very famous models that is also called the LV models. In this model, the time variable t is greater than 0, and the vt and the wt is present the densities of the prey and predator population. Now we just replacing the integer derivatives into the fraction one. It becomes a fractional model. It's called the fractional LV models. And in this case, we are choosing the CF derivatives, which we show in the next slide. And the fractional order is between 0 and 1. Well, the CF derivatives is nothing but changing the kernel in the capital derivatives in the other ways. And also for the simplicity, we just consider the normalized function CF cosine is equals to 1. Next, we are going to introduce a numerical method called the three-step Adams-Bedford scheme, which can easily solve the math models under the CF derivatives. And during some formulas evaluation, the results of this form is look like this. And I also provide the three-step Adams-Bedford method in the algorithm form in my paper. At last, I'm going to give a numerical experiment about the fractional pre-predator models, that we consider the coefficients as follows and give the initial point. And I set the fractional order cosine equals to 0.7, 0.8, 0.9 to the 1. And now let's see our numerical results. We can see that as the Casey is getting closer to the integer one, the curved solutions are also approached to the integer one orders. And as the Casey increases, we can see more carefully how the fractional order of the time derivative affects the population growth. At the last, I would draw a brief conclusion about what I have done in this project. At the first, I studied some various definitions of the fractional derivatives. I mainly studied the GL and capital derivatives and studied their numerical performances on the sin x, x squared, and exponential x. And from the numerical performances, I find that if there are some issues in the exponential x, then I'm going to analyze the GL and capital derivatives on the exponential and trigonometry functions. And the result is that just by changing the range of the valuation, the result is changed as well. So it reveals a property of the fractional derivatives that it is non-local, while the ordinary derivative is local. Then I provide the application of the fractional derivatives that I solve one fractional pre-predictor model, which is also called the FLB models. By applying a numerical method called the three-step Adams-Bedford method, I provide a numerical experiment choosing the fractional order Casey equals to 0.721. From the numerical results, it can be shown that when the fractional order is approaching to the integer one, the curve of the solutions is also approaching to the integer ones. In the future study, it can be exploring other effective numerical algorithms on solving the fractional models. And now it is the end of my presentations. Thank you for your listening.